we are going to study atomic and molecular structure, and today in the lecture 3 we are proceeding further with the MOT of a few more molecules. So, I am Dr. Manisha Shukla, continuing with MOT of oxygen molecule, molecular ions of oxygen molecule, MOT of heteronuclear diatomic molecules, nitrogen monoxide as a heterodiatomic molecule, carbon monoxide molecule as a heterodiatomic molecule. We are also going to take up hydrogen fluoride molecule and the cyanide molecules. So, all these molecules as per your syllabus are quite important, and till now we have studied the homonuclear diatomic molecules. Out of the homonuclear diatomic molecules, oxygen is one of the very important molecule which we are going to take up today in lecture 3. So, if we have a look at oxygen, firstly the number of electrons which are found in oxygen, 8 electrons. So, number of electrons in oxygen being 8, so it has 8 electrons. Now, when the oxygen molecule is formed, it has a total of 16 electrons. Now, let us distribute these 16 electrons according to molecular orbital concept. So, these 16 electrons when distributed will occupy sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2. Now, the point to be noted, in lecture 2 the last molecule which we taken was nitrogen. Nitrogen, which has atom nitrogen, has 7 electrons. So, the diatomic molecule of nitrogen has 14 electrons, and as discussed earlier, for the 14 electrons the configuration, the MOT configuration followed is so wherein the pi 2px and pi 2py get filled first and sigma 2pz gets filled later. And I also explained to you the fact for why this kind of an anomaly is observed is due to a lesser stability of the nucleus, and therefore, the sigma 2pz getting destabilized and hence getting filled after pi 2px equals to pi 2py. So, this was the case of nitrogen. But oxygen onwards, since we have moved to the total number of electrons above 15 in the molecule, so the normal sequence of filling up as per the Aufbau's rule will be followed. तो यहाँ पर अब ऑफबॉ के नियम के आधार पर जिस प्रकार से मॉलिक्यूलर ऑर्बिटल्स को फिल किया जाना चाहिए वही रेगुलर सीक्वेंस फॉलो होगा. अब हम देखते हैं कि ये जो 16 इलेक्ट्रॉन्स हैं दे आर डिस्ट्रीब्यूटेड अमंगस्ट sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, then pi 2px equals to pi 2py, both have 2 electrons in it. Now, if you add it up to here, it accounts for 14 electrons. Now, the 15th and the 16th electron will occupy pi star 2px equals to pi star 2py. Now, since both these orbitals are equal in energy, therefore, they will first be occupied singly, and if an extra electron is added on to it, then the pairing will take place. We all know that very well from the previous knowledge. That means the Hund's rule, the Pauli's exclusion and the Aufbau's rule, according to which the MOs are also fulfilled. So, what happens is that when the orbitals are of the same energy, they are first occupied singly, okay, and then the pairing takes place. Okay. So, therefore, now pi star 2 px equals to pi star 2 py, since are singly occupied, therefore, there are two unpaired electrons found in the oxygen molecule. Now, when we discussed the limitations of VBT, we very clearly put forward a concept that one of the reasons for why VBT failed was its inability to explain the magnetic character or the paramagnetic nature of the oxygen molecule. Herein, the same thing has been taken care of. Now, how has it been taken care of? When we discuss paramagnetic molecules and said what type of molecules are paramagnetic molecules, the molecules which have unpaired electrons. So, though oxygen has 16 electrons in all, yet since the pi star 2 px and pi star 2 py are singly occupied, so there are two unpaired electrons in it, and hence the molecule will show magnetic character and O2 becomes paramagnetic in nature. Let us find out the bond order of O2. Number of bonding electrons minus number of anti-bonding electrons divided by 2 will give us the bond order. Now, let us total the number of bonding electrons. 2 plus 2 4, 4 plus 2 6, 6 plus 2 8 and 8 plus 2 10. So, 10 are the bonding electrons. Number of anti-bonding electrons 2 plus 2 4 and 2 more are 6. So, therefore, the bond order is 2. Now, since the bond order is 2, oxygen molecule, therefore, as observed, the molecule has two unpaired electrons in its pi anti-bonding MO, and hence the molecule shows paramagnetic nature. Now, one of the question, a very important question which may appear is that the question is like, you have to compare between N2 and O2, either with respect to the strength of the molecule. N2 is stronger than O2. The reason why N2 is stronger than O2, we just learnt in the previous lecture that N2 had a bond order, N2 had a bond order equals to 3 and O2 has a bond order equals to 2. So, therefore, higher the bond order, stronger the molecule. Okay. So, the answer to this particular question. Another question which appears in the exam is that O2 is paramagnetic though it has even number of electrons, whereas N2 is diamagnetic. Now, if you remember the previous lecture, N2 had all the electrons which were paired, whereas O2 has unpaired electrons, and therefore, it explains why O2 is paramagnetic and N2 is diamagnetic. So, these are two very important questions which appear in the exam. So, let us take up the molecular ions of oxygen, just like we took up the molecular ions of nitrogen, and a very small question appears on this particular fact also, that you in your short questions and as well as long questions, this particular question is asked. You are given a number of ions or molecular ions and you have to compare them with respect to stability, you have to compare them with respect to the bond strength or the bond length. So, this sort of a question is also asked in N2 as well as O2. So, let us look at a few popular molecular ions. So, we have the first one is known as superoxide and the second one is peroxide. You can see it here also, superoxide and peroxide. Now, superoxide has one electron extra, that means you have O2 and you add one more electron to it. So, therefore, only O2, that means the normal oxygen molecule had 16 electrons in it. Okay? The normal oxygen molecule had 16 electrons in it. Now, when we have O2 minus, that means total number of electrons are 17. So, the extra 17th electron will occupy, now you can see it in blue, the extra electron which entered the molecule is present over here. So, this is the molecule which is present over here. Okay. So, therefore, since the electron goes into the anti-bonding MO and the bond order therefore becomes, now we have omitted the first energy level over here, the Kk star, and therefore we have written 8 minus 5 and the bond order is 1.5. You can calculate it from here. The bonding electrons 2 plus 2 4, 4 and 4 8, 8 electrons, the anti-bonding 4 and 3, 2 and 3 5. Okay. So, the bond order is 1.5. In the similar manner, if you have 2 more electrons entering it, and this particular is known as peroxide. So, in case of peroxide, the electrons occupy the anti-bonding, that means the pi star 2px equals to pi star 2py, both get paired. Both of them are shown to be paired over here. Okay. Now, superoxide since has one unpaired electron and hence it will be what kind of a magnetic property? It will be paramagnetic in nature. The peroxide has both the electrons paired in the outermost MO as well. So, the magnetic character it will show is diamagnetic character. Let us find out its bond order. So, you can calculate it from here, 2 plus 2 4 and 4 8 bonding electrons, and the anti-bonding electrons are 2 and 4 6. So, therefore, the bond order is 1. Similarly, in the same way, you can also look for O2 plus. You can also look for O2 plus. Now, since O2 has 16 electrons, so therefore, O2 plus will have 15 electrons. Okay. Now, if it has 15 electrons, that means 1 electron less. So, this is your O2 molecule, and for 15 electron, one of the electron which will go from here. Fine. So, the anti-bonding will have 1 lesser. The anti-bonding will have 1 lesser. So, if you have to find out the bond order of O2 plus, so it will be number of bonding electrons are 2 plus 2 4, 4 and 4 8 minus the anti-bonding electrons will become 2 and 1 3, and this will be 5 upon 2 and the bond order will be 2.5. Okay. So, in this way we can compare the molecular ions. When we compare the molecular ions, so let me write O2 plus also over here, O2 plus also over here. So, when we compare the bond strength, so since O2 plus has the maximum, so you know I can write O2 plus followed by O2 followed by O2 minus followed by O2 minus minus. So, this is how we can compare the stability, and bond energy also will be in the same order, but if you have to write down the bond length, it will be in the reverse order, because bond length is inversely proportional to bond order. So, this is how we are going to take up the oxygen, the molecular ions of oxygen. Now, let us move on to the next topic. Up to oxygen we have studied, and I hope things are clear to you up to oxygen. Heterodiatomic molecules. So, heteronuclear diatomic molecules, one thing very important, that is when we draw the MODs of heteronuclear diatomic molecules, the diagrams are a little skewed or tilted. Why? Because the electronegative atom or whichever atom has more electronegativity has comparatively lesser energy. So, on an average when we draw the structures, then these structures are slightly slanted, slightly tilted. Okay. Let us have a look at NO molecule. NO molecule has in all 7 plus 8, that is 15 electrons. Let us distribute the 15 electrons in its various MOs. So, when we distribute it in various MOs, leaving the first energy level Kk star, otherwise sigma 1s2, sigma star 1s2, then sigma 2s2, sigma star 2s2. So, that makes it 8 electrons, followed by pi 2px equals to pi 2py, both occupied by 2 each, another 4 electrons into it, and then sigma 2pz has 2 electrons in it. The 15th electron will enter pi star 2px as seen over here. Now, let us calculate the bond order. Let us calculate the bond order. So, therefore, let us calculate the bond order. While calculating the bond order, number of bonding electrons minus number of anti-bonding electrons divided by 2 will give us the bond order. So, that means 2 plus 2 4 and plus 4 will make it 8, and 8 minus 3 divided by 2, and that is 5 upon 2, and the bond order is 2.5. The bond order is 2.5. This will be the bond order. Okay. Now, NO, and now since there is one electron which is found as a lone electron or the unpaired electron, and therefore, NO will show what kind of a character, magnetic character, paramagnetic character. Okay. It contains an unpaired electron in its pi star 2px or 2py orbital. Similarly, we can have the molecular ions of NO also, that is NO plus, where one electron is lost, that means 14 electrons are there, and we can have the molecular ion as NO minus also, where, so the NO plus is quite the same as 14 electrons means N2, and NO minus, which will have 16 electrons, will be quite the same as O2. Okay. But while writing the sequence or while writing the electronic configuration or drawing the MOD, it will follow the same sequence as its parent. The sequence is maintained in the same manner as the parent molecule, and the parent molecule is NO, and NO which has 15 electrons, and these 15 electrons, okay, these 15 electrons in the NO will not be what? Following, I mean, if you reduce one electron, that does not mean that it will start following the anomalous sequence wherein we fill up the sigma 2pz before sigma 2pz that way. Okay. So, remember one thing, that whatever is the parent sequence, that parent sequence will be followed. Okay. So, that is the condition. Now, the next molecule is the CO molecule. Now, let us have a look at the CO molecule. When we have a look at the CO molecule, carbon has 6 electrons, oxygen has how many electrons? 8 electrons in it. So, carbon has 6 electrons, oxygen has how many electrons? 8 electrons. In all, it has how many? 14 electrons. So, let us fill it up. Let us fill up the MOs for it. So, if we start filling up the MOs for it in a normal manner, in a regular manner, and try to find out its bond order. So, in case of CO, and if we try to write its molecular ion and then compare. So, under the normal condition of filling up the MOs in the CO molecule, if you observe it very sincerely and carefully, whatever I have written over here, the sigma star 2s, if we write the regular sequence, then it should have appeared over here. The sigma star 2s in a regular sequence should have appeared over here. And it is, of course, we can calculate its bond order would come as 3. But the problem arose when we studied CO plus molecule. And when we went ahead to study CO plus molecule, it was observed that the CO plus molecule has a shorter wavelength, has a shorter bond length compared to CO. Now, had it been that the CO molecule and the CO plus molecule followed a regular trend, then the electron which would have been expelled from it would have been expelled from the bonding MO. Now, if the electron is expelled from the bonding MO, then you always have a lesser bond order. That means, the anomaly in this particular CO molecule is that due to large electronegativity difference between C and O, due to a lot of electronegativity difference between C and O, their electronegativity difference is so high that the molecule is so much so tilted, the molecule is so much so skewed that sigma star 2s gets so highly destabilized that it appears much above the sigma 2pz as well. And now when the electron is expelled for the formation of CO plus, it is expelled from the anti-bonding MO, and hence there is an increase in its bond order. And therefore, normally what is observed is the bond length of CO plus is found to be lesser than the bond length of CO plus is found to be lesser than that of CO. And because of this reason, because of the anomalous behavior that sigma star CO, the sigma star 2s MO gets filled after sigma 2pz, and that is because of the high electronegativity difference between carbon and oxygen. The difference is about of 1, and this high electronegativity difference causes this kind of an anomalous behavior. So, normally CO which has electronegativity of about 2.5 and O which has an electronegativity of approximately 3.48 and the electronegativity difference being approximately 1. So, this molecule is highly skewed, highly tilted, and sigma star 2s gets so destabilized that it is written above, This can be seen above sigma 2pz as well. Now, for this reason, this molecule CO has a lot of importance, and therefore, it is written in this manner. The next molecule is the HF molecule. The next molecule is the HF molecule. Now, for HF molecule, H has 1s and F has 2p which has electrons in it, and the electronegativity of the two is so much so different for hydrogen and for fluorine. There is so much of electronegativity difference between the two that because of this reason, it is the 1s of H is not even comparable to the 2p. The only partial overlap which can be effectively obtained is between 1s of H and 2pz orbital. The rest of the two pair of electrons present in the p of fluorine remain in the non-bonding MO, and the only possible formation is between 1s of H and 2pz of fluorine, and this kind of a bond formation takes place in HF. So, as in hydrogen fluoride, the hydrogen 1s orbital can mix with the fluorine 2pz orbital to form a sigma bond only, and therefore, The rest of them do not participate in much of its activity, and the bond order is found to be 1. And since all the electrons are paired, and therefore, this also remains as a diamagnetic molecule. And now, the next heterodiatomic molecule is Cn, and Cn minus, since is more stable, therefore, I have taken Cn minus as for the diagram. In case of Cn, carbon has 6 electrons, nitrogen has 7 electrons, you add them up 13 electrons. Okay. Now, the electronic configuration as mentioned herein. Now, have a look at its bond order. So, the bond order appears to be 2.5, and there will be one unpaired electron in it, as you can see over here. Now, since sigma 2 pz has an unpaired electron, if extra electron enters it, this also gets paired up. An electron added to the bonding MO always strengthens the molecule, and therefore, Cn minus is more stable compared to Cn. As you can see, it has got paired up, bond order is 3, which is more, and therefore, more stability. Now, the diagram I have drawn over here is of Cn minus, as you can see over here. So, this is how the MOD of Cn minus will appear. So, these are some of the molecules which we have to study in our syllabus. In our syllabus, HF is quite important. So, you must draw and practice the HF molecule. Okay. You must practice the CO molecule as well, and of course, NO molecule is also an important molecule to be practiced. Okay. So, therefore, we have studied heterodiatomic molecules also today. So, thank you very much for being a part of this class. I will expect all the children to kindly draw the MODs and practice them accordingly.